This lesson's really important. And I'm actually okay if you don't understand how important it is right now, just right now, because there's so much more meaning to finding the displacement of the position if you are just given the velocity. You don't have any initial positions. Uh, what we have to do is understand this is a derivative. We take the antiderivative to find a position function. We have this plus c. We don't know what the c is. Well, turns out it won't matter because if I know my position at time 1 is 2 plus c, and I know my position at time 3 is 12 plus c, guess what? I know my displacement of position is plus 12, plus 10. You just like end right there and just do the rest of these problems and be fine with it. Without really understanding that, what you actually found was an accumulation of something. You found the area under this shape, which is really like so crazy that we found an area by just using an antiderivative that they call it the fundamental theorem of calculus. It ties together like accumulating in sums with antiderivatives, seemingly two completely different things. And like I used to teach students, like just like here's what it is, and just like do this, take the antiderivative, and oh, you're gonna have a plus c, and don't worry about the c, and then you plug in 3 and plug in 1 and subtract. But now I teach students, hey guys, we really just have the situation we've been dealing with since a long time ago, that if we understand the signs of a derivative, now let's say we don't even know, but we actually understand, a position's going to increase or decrease based on the sign of its derivative, and we figure out this, well, obviously we can figure out the accumulation of my derivative, my meters per second, by subtracting the two numbers. And so it's like, oh, most likely this is more positive than it's negative, which means like this is going up. This is how much it goes up. And that's kind of how we connect it with stuff that makes sense to us. But we are just finding an accumulation of a derivative, an area, using an antiderivative. So like you don't even have to write this anymore. You don't even have to go like write this. You could just go straight to the accumulation of my derivative if you want to do this, or you could just say my displacement comes from the change of my position. And I know my position at 3 and my position at time 1, and I'm just going to subtract them. So I started at C, I went to -6 plus C. This equals -6. So overall I went, and what does this mean? What does displacement of position? And I liked what one of my students said earlier. At the end of the day, I ended 10 to the right of where I started, or my accumulation of my derivative, my accumulation of 2t plus 1 from 1 to 3 was 10. My accumulation of my derivative from 1 to 3 was -6, or at the end of the day, I end up 6 to the left of where I started. And like, this is the big question. Hey, Clayberg, how's it going? You're on my YouTube video. Yeah, You want to be in it? Say hi to everybody. Hey, cameo, Claimer cameo. Okay. Uh, this is like the question that we talked about. It's like if I asked you what is the area under t squared or x squared from 0 to 2, and like you'd be like, I have no idea, but you can think about it just like what we've been doing. Well, if we think about this as a derivative, we say the accumulation of our derivatives are meters per second over the interval of seconds. And I can find that by finding the displacement of our positions, our meter positions. Uh, and we figure out that I started at C and I got to 8/3 plus C, that my displacement was 8/3, or my area under x squared from 0 to 2 is 8/3. It's like we usually have to use geometry to find areas, not here. Not cool? I don't know which way I like better. Getting the end minus the first, or first and the end and then subtracting them. 0 is my answer. I started at C, I ended at C. At the end of the day, I have not displaced at all in my position. Doesn't mean I didn't move. And that's what we're going to get into in the second page and the third page when we talk about distance. This is just a great question. Like, it's an amazing question, and you might not appreciate it if you just say, oh, I just need to take the antiderivative, find the change in my position, that's displacement, instead of thinking about it in terms of like area. So if you think about this in terms of area, what did we just find? We found that the area under 6 sine t, which pops all the way up to 6 after pi, the area under 6 sine t is what? Well, it's this displacement, which gives me the area under the derivative, 12. The area under 6 sine t is 12. The area under just sine t is just 2 from 0 to pi. One hump of sine. Cool. And again, you could always think about this in terms of my derivative is positive, my position is increasing. If I know my position at 0 and 1, I'll know how much it increased. Well, now we talked about how much it increased is actually equivalent to accumulating my derivative. Now we're going to find how to accumulate your derivative without kind of having to accumulate by taking an antiderivative. And if you're just copying this down, it's I don't care. Like, you don't know what you're doing. The next class is important. The following class is important. Try to slow it down so you understand. Oh. If I plug in 1, I get positive 6 over pi plus c. If I plug in 0, I get negative 6 over pi plus c. If I go from negative 6 over pi plus c and I go to positive 6 over pi plus c, I've increased 12 over pi. I don't need the plus c's because They're the same number. How would the work change if I had an initial position? Let's go back to 2t plus 1. Okay, let's go back and said, oh, actually, I know that the position at time 1 was 3. I said position at time 1 was 4. Well, if the position at time 1 was 4, then this is 4. Actually, position at time 1 is 4. I mean, C is 2. Because I plug in 1 for T. And I got 2 plus C equals 4, and I get C equals 2. Okay, so C is 2. Well, does that change anything? The answer is no. Like, my position at time 1 would just change to 4. My position at time 3 would change to 14. Yeah, but still 4 to 14 is still 10. Doesn't change it at all. What about in the other situation? If I have 3t squared minus 16, position at time 3 is 18. If my position at time 3 was 18, well, that means C is 18. Well, that means like my position at 0 is 18, my position at 3 is 18. It doesn't change at all. So doesn't change the displacement, but at least we do know exact locations. Cool. Now, the next questions are questions where it's like, okay, cool. We know how, at the end of the day, how far we ended up versus where we started. But how far did we travel to get there? And the key to understanding this is doing what we do so often, is do a full sign analysis of our derivative. How do I do a full sign analysis of our derivative? We take our derivative, we set it equal to 0. We plop down the time. We plop down our start and our end now. This is my derivative. I use some test points. I plug in 1 and I get positives, and I plug in 2.5 and I'll get negatives, because it's negative 2.5 times negative 2 plus 4. And we see our position increases, then decreases. Cool. Well, to figure out how far I've traveled, I need to figure out this number, and I need to figure out that number. And then I'm going to use something that a lot of students intuitively understand, just makes sense, an absolute value, to make my positive displacement, keep it a positive displacement, take my negative displacement and make it a positive displacement. So we got to do that. Where I get the position is negative t squared plus 4t plus c. And I know my position at time 0 is c. Great. My position at time 2 is negative 4 plus 8 plus c. So that's 4 plus c. And then my position at time 3 is negative 9 plus 12 plus c. So position at time 3 is 3 plus c. And I remember I kind of looked at negative 2t plus 4 from 0 to 3. Did I? No, I didn't. This is like on our lesson. And I would say my displacement from 0 to 3 of position, from 0 to 3, is 3. I ended up 3 to the right of where I started. But through a further analysis, we realize we go to the right 4, we go to the left 1. I go from C to 4 plus C to 3 plus C. I have a distance of 5. If my position at time 0 was 4, would it change any of my answers? No, it would just tell me that I go from 4 to 8 to 7. So at least I know exactly what my answer is, But like, would I add this 4 to 3? No. Would I add the 4 to 5? No. No, it would not change any of my answers. I don't take this value 4 and add it anywhere. It just changes my numbers that I have to get my calculation. Same thing. Here's my derivative. Do the full thing. Understand the signs. Here's my position function, which I take the antiderivative find. If I plug in 0, I get C. If I plug in 2, I get 12 minus 8 plus C, which is 4 plus C. If I plug in 3, I get 27 minus 12, I get C again. So a very good question, because I start at, I guess this is very similar to what I had, C. I get to 4 plus C, but then I end at C. I increase 4. I decrease 4. Overall, my displacement's 0. My distance is 8. If my initial position was 1, would that change anything? No, it would just turn this into 1. This would be turned into 5, and this would turn back into 1. I would still have a distance of 8. Yo, I'm given the distance. I'm given the position. I'm given F. I'm given P. How do I find how far I've traveled? Guys, you have to analyze your derivative. We are using our derivative to really understand how our original function is changing. You want to know how far your position changed, how much total? We got to look at our derivative. We got to figure out the signs. We got to figure out then my positions at 0, 3, and 4. My position at 0, my position at 3, negative, it's 9 minus 18. It's negative 9 plus 1, which is negative 8. My position at 4 is 16 minus 24 plus 1 minus 7. So I start at 1. The accumulation of my derivative is minus 9 and then plus 1. So 10 is my distance. Overall, I ended up 8 to the left of where I started, minus 9 plus 1. But to get there, I'm on the y-axis, so my positions decreasing means I'm going down. Positions increasing means I'm going up. 9 minus 18 is negative 9 plus 1 is negative 8. 16 minus 24 plus 1, negative 7. Cool. You can always check. And how can I check? What if I accumulated my derivative? Minus 8. Good. What if I accumulated the absolute value of my derivative? what you could actually do is you could look at your original equation. I wouldn't recommend doing this, but y equals t squared. I shouldn't do this at all, honestly. Minus 6t plus 1. And you can see that you started at a position of 1. You decrease to a position of -8. And then you increase to a position of -7. Like, there's your positions at times. So, displacement, or you ended up 8 to the left of where you started, but you traveled left. Sorry, 8 below where you started. You traveled down 9 and then up 1. But that's not the big deal. The big deal is like understanding how you could do it really quickly with a calculator. What have we been doing this entire time? We were taking these negative displacements, making them positive. We're adding, we're accumulating things as positives instead of as negatives or positives. We want positives to stay positives. We want negatives to turn into positives. You could always, with a calculator, accumulate the absolute value, and that will give you a distance. You can check all of your answers before earlier using your calculator and double checking. It's always good to double check. Giving you the acceleration. What's the distance the particle traveled from 0 to 3? Well, I need to do a sign analysis of my first derivative. That's my second derivative. I got to go backwards. I got t squared plus c. My initial velocity is 4. Cool. I wish it was -4. I wish it was -4, but it's just 4. Well, there's something, a reason why I wish it was -4, because your derivative is going to be just positive from 0 to 3. You have t squared plus 4 never equals 0. You'd have the square root of a negative. You don't have that. So your position's increasing. Here, well, this is a good example of displacement and distance will be the same when velocity is positive. Position at time 0 is c. Position at time 3 is 27 times a third is 9 plus 12 is 21 plus c. So the displacement equals the distance, which equals 21 plus 1. I'm going to write that down. Displacement equals distance, which equals 21. Well, if you need to, your derivative is positive, then negative, then positive. Your position increases, decreases, increases. It increases by 5, it decreases by 3, and increases by 1. Overall, my displacement, you could add these up together, or you could consider your position at time 0 to be c, which means your position at time 3 would be 5 plus c, which means your position at time 5 would be 2 plus c, and then your position at time 6 would be 3 plus c. Overall, 3 is my displacement at the end of the day I ended up 3 to the right of where I started. What was the distance? 9. You can accumulate all those positive displacements. Accumulate your speed times time. Your positive meters per second times seconds. Yeah, even if I have x of 3 equals 2, it doesn't matter. I go left 2, right 6, left 3. I displace 1, but I traveled 11. My position at 3 doesn't make a difference when I'm talking about displacement or distance traveled. Sure, maybe you could go, and many of you need practice, finding your position at time 4. Well, the position at time 3 is 2. Position at time 4 is -1. If I increase 6 to get to 2, I must have come from -4. If I decrease 2 to get to -4, I must come from -2. -2 minus 2 is -4, plus 6 is +2, minus 3 is -1. All these numbers work with each other. But look, overall, at the end of the day, I'm 1 to the left of where I started, or sorry, 1 to the right of where I started. I went from -2 to -1, plus 1, but I went left 2. I went right 6. I've traveled 8. I went left 3. I traveled 11. We got these answers earlier, right? Distance, 2t plus 4. Okay, good. So we got these answers. We're looking for an answer of 5. 5. 3508. Okay? 3508. We already know this is 3, and the distance is 5. We did it without a calculator. We already know the displacement is 0 and the distance is 8. How can we find that quickly without a calculator? Well, we can just accumulate your meters per second times seconds. We can accumulate your positive meters per second, your speeds. Velocity times time, speed times time. Done. Same thing here. So let's just see. Here's the displacement. Add in an absolute value. You can just copy paste, then go to your keyboard and go absolute value before and absolute value after V. You could do it after the DT, that would work as well. Oh, no, they don't let you do that. There, 5. Then, boom, what if it was 6t plus 3t squared? Minus 0, 8. Just like I expected, 0, 8. Would anything change if I had an initial position? Distance would not change. If I had an initial position, you might be like, oh, do I have to do 4 plus? No, it's just a location. It would not affect how far we've traveled, just like I tried to show you over and over and over again. And hopefully you understand. And if you don't, you're probably not listening anyways. Don't have to do a full sign analysis. You can if you want to. Like, there's a lot of stuff that we could look at to confirm things. But I just want this homework video to be done. It was a frustrating day today, guys. $10.25. 6.111. For real? Look at that. Now you know that your velocity and your speeds are all positive. $2.25, $10.25. Two different things. Okay, cool. All right. Next class, overall maxes and mins. Absolute extremo. Much shorter video. Peace.